Hello, folks. I'm Nathan Hall, and I'm going to be taking you through the Command Line 101 training. Just to tell you a little bit about myself, as part of my day-to-day, I use the Command Line pretty much all the time. I'm a computational biologist and really like introducing folks to the Command Line because you get so much power out of it. So we're going to go ahead and I guess just get started here. So first of all, the reason we're using the command line is so that we can access Linux computers. And the reason we're using Linux is because it's a nice open source programming language, operating system. It's often well documented. It's excellent with handling large data sets with minimal computational overhead. And what that means is that you can open up very large files and stream through them quite efficiently on your desktop or even up on a server without, say, opening Excel. Now, Excel does have its own benefits and uses, but whenever you're trying to stream a million lines of data, it's nice to have something that's a little more efficient. Most servers and HPCs use Linux. Also, if you're using cloud resources are frequently built around Linux distributions as well. If you downloaded MOBA Xterm onto your computer, is that Linux? It's a way to interact with Linux if you have it installed on your computer, but it's not itself it's not a full operating system. So that also brings up another point. We went through quite a bit putting together SSH keys if you showed up to the virtual meeting. And we're not using that today. And part of the reason for that is because whenever we want to stress test our AWS distribution, they maxed out at 8, even though we were hoping to get all of 200. And so we can't really do training with just 8 people having access to the resources. So for this session and all the sessions that you'll attend, it'll be mostly a display. And we're going to walk you through it. And because it's being recorded, you can come back and do the commands yourself. So that's where we're at right now. So I've talked a little bit about Linux, and I want to talk a little bit about the command line. So Linux is a whole operating system, and a command line is a specific way of interacting with your operating system. Here, if you see on the side of the screen that I'm hitting enter on, you should be able to see that we've got command prompt here. This is a bash shell or born again shell on a remote Linux machine. If you have a Mac, you're actually using a Z shell, which is related to bash, but through its original distro, the Bourne shell. All that to say is that if you're using a Mac, you're using a variant of Bourne shell that is very closely related to bash, and most things will translate pretty directly. So in this course, what we're going to do is introduce you to some basic tools that are used in bash, and these will be accessible to you whenever you use your Mac. You could use them around the house or in your own sort of research there, or whenever you're using remote machines, or if you're using a Linux machine. If you have a Windows machine, you can actually turn on something called Windows Subsystem Linux and use Linux on your Windows machine, something that I found very useful whenever I was using a Windows machine. So getting oriented, through the next set of slides, what I'm going to do is display a set of questions and then go about sort of answering them on the command line and giving examples of how to do it. What I want to model for you today is first the commands, and then also whenever you jump into a new command, what are some basic things you can do to get a sense of what that command does, because you're going to want to be able to figure out how to add tools to your bash toolbox as you go. So first of all, you can see that I'm on the command line, and you want to know some basics about yourself. First, you want to know who you are. And so who you are in terms of the computer, you can type in who am I, and it gives you back your username. So you can see that it says EC2 user. So I've logged in to this AWS EC2 instance, and it's creatively named me EC2 user. Where are you? So where am I within the actual file structure of the computer? I can figure out where I am by printing my working directory or using a command print working directory. And it tells me that I'm in home, and then that I'm in a file or in a directory that's named for my username. And this is traditionally where you end up whenever you go to home. What groups do I belong to? Groups are important because whenever you join a computer, whenever you have people on your computer or server, what you can do can be limited by your groups. And so you can see here that I'm in my own group to begin with, and then I'm also in an admin group and several others as well. It actually tells me that I have quite a bit of power. Groups are something that you can go back and check to make sure if you don't have access to something, that you can get it by either changing your groups or changing the groups to which something is. How can you tell if you have access to something? Well, we can list out everything and then do a long list. If we do a long list, it gives us these guys right over here. So this string of letters is actually a set of permissions, and it tells us about the file. The D tells us it's a directory. And then these first three letters tell us that the user or the owner of the file can read, write, and execute it. That's good. These next three tell us that the group that the user's in can read, write, and execute it. And then these last three are anyone who has access to the computer. So these are the most permissive. And it tells us that anyone who is on the computer can read, not write, and execute it. So you can execute a directory because you can go into it. But it does mean it's nice because it tells us that just because you're on the computer, if you're not a part of the group or you're not the owner of the actual file, you can't write it. So write would be a way that you could say delete something. So by looking at the permissions, knowing your groups, knowing who you are, you can determine if you have access to something. So if we cd to root and we list everything out, you can see that it's listed out for root, and then the group is root. And it's really not very permissive up here. For example, the boot disk, that looks pretty important. Everyone can execute and read it, but nobody can write to it. And that seems like that's appropriate because you could really mess something up. So whenever you're talking about root is essentially the computer. And what root's trying to do is protect the computer from you and from me. And so by doing that, it changes the permission. So if you get errors that say you don't have permission to write here or whatever, you should check where you are. It turns out that whenever we're in the root directory, we're in a really pretty high powered directory. So we want to go somewhere else. When we go somewhere else, we can do a couple things. We can type the command change directory, cd. And if we don't type anything after change directory, it takes us back to our home directory. How can we verify that? We can type print working directory, and sure enough, here we are. We can look around in our working directory. ls, list everything out and see the things that are there and confirm that not only are we where we are, but we have access to what we have access to. So what you want to think about here, the last question is what is path? So a path is a way to get to a file, and whenever you're trying to access the file, you can have a relative path. So like if we wanted to cd into studies, we could type cd studies, and that would be a relative path. Because once we cd into studies, we can't cd into studies again because there's no such file or directory. We listed out, sure enough, there's no such file or directory. That's because it's a relative path. Well, let's go back to working directory, and we can use an absolute path. So an absolute path will work no matter where you are in the actual computer. So we can say cd, we can say home, we can say ec2 user, and then we can say studies. Well, okay, that worked. We can actually bring that command back using the up arrow and do it again. And it doesn't really get us anything, but it does let us know that we can actually get there. Because we don't get an error, and sure enough, we are in studies. So those are the basics of moving around within a computer. What you can do is you can cd for change directory. You can ls, and so you can list out the files that you can see that are like immediately close to you. And then you can print your working directory, and that tells you where you are. So as we get going, one thing that makes this whole caper a little bit easier is having some good shortcuts. And I'll start with my favorite shortcuts, and these are the ones that I use quite a bit. The first one is Control E, and the second one is like a Control A, and that's just going to the beginning or end of the line. So if I have some line like, let's say, cd, the cd command, I can hit Control A and go to the beginning of it and type something like echo. So now we can do something with that. Or I can go Control E and go to the end of the command. So that's pretty cool. So Control A takes us to the beginning, Control E takes us to the end. Maybe you got to the end of your command or the middle of your command and realize that you're not in the right spot, or you need to do something else. To store that command and kind of like put it in the background so you can move around a bit, you type in Control U. Now we can cd somewhere else, like the terribly important, oh, not there, root directory, ls, pwd. And then you can actually bring it back with Control Y. Did that do anything for us? No, it didn't. Why not? Because we put echo at the beginning. So we can go back to the beginning, remove our echo, and then hit enter. One thing I want to highlight with these commands is that you can hit enter from anywhere in the command and it will execute it. It doesn't move it to the next line. So this is important just for like your own sort of command line control. If you're in the middle of something and hit enter, it will go to the next line. Another thing to be careful of, particularly copying and pasting, is often you'll copy and paste a line return without realizing it. And if you copy and paste a line return into your terminal will immediately execute it. So just be careful with that. Control R is pretty nice. Control R lets us search our history, and it actually brings back the last command that we used our search term in. So we can get like an egrep using Control R. See, it looks like I used something. Wow. Okay, so someone actually on this used for sample in. Yeah, that was not me. That's kind of fun. You have it. So what are we doing there? We're searching the history. And so this is a good idea to know your history, To see your history, you can type in history, and it'll print off everything it's saved for you. You can make your histories heinously long and save all sorts of stuff in there, but typically histories are fairly short. So as you think about saving your commands, the best way to do that is to keep a notebook separate instead of making your history heinously long. If you do opt for using your history to save all your commands and refer back to it, one thing to be aware of is your history won't tell you where you were when you executed that command. So keep that in mind. Something that I've been doing, but maybe not explaining very much, is you can up arrow. So actually just pushing the up arrow on your keyboard, and it brings back the commands that you've done before. Now this is very nice, particularly as you're building commands. You can type a command, see how it works, up arrow, and then keep building onto it. And I'll demonstrate how that's done a little bit later. The last two are perhaps my most favorite, and they make the command line much more user-friendly, and it's called tab completion. So when we're here and we want to type CD and we want to see what's available, instead of like hitting Control U, listing it out, Control Y, bring it back, and then type in something. Then type in, I can't not do it. One way to get around typing in something is hitting tab. So you see we have capital M module 2 or lowercase m module 1. If we type in capital M, lowercase m, and hit tab, it completes. And it completes because that's the only option for it. This is pretty nice. It works for programs as well. So if you wanted to use, like, say, conda for something, you can see all the things that start with con. There's a continue, a convert quota, which sounds pretty interesting. But here we'd just be looking for conda, env, and conda. So tab completion is helpful. If it doesn't complete on the first tab, you hit tab again, and then it gives you a list of things that it can be. So double tab to display your options. And that's going to be very useful, particularly as you go about writing your commands, moving through your directories, because it saves you so much time, and it also makes sure that you don't get typos. So now what we're going to do is break down the command prompt a little bit. You can see the command prompt over here, and I've taken a nice screenshot of it here. And we'll just talk about everything that we see from base to everything contained in the square brackets. So in the base, what we're seeing right up there is, oh, nope, wrong enter. What we're seeing right here is telling us that we're actually using a program called conda. And so I want to tell you a little bit about that, because conda ends up being very nice for you on the command line and is quite a nice way to handle bioinformatics software. And the reason for using the command line as biologists is because it gives us access to the cutting edge biological software. And a lot of that is served through conda. So what does base mean? Base means that we're in the basic conda environment. So conda has different environments that you can make, and we can actually list them out. So if we list them all out, type in conda env list, it shows us with this asterisk that we are in fact in base. It also shows us that we have another environment called Blast Plus, one called Callisto, and one called SAM Tools. And in each of these, we've installed a program, SAM Tools, Callisto, Blast Plus. It could be that you have a project, and so you could make a Conda environment for that project. So we could say Conda create, give it a name, and let's just say it's command line 101, CL 101. Well, let's do I for interface, command line I 101. Okay, so do we want to add it? We can add it, of course. So now it tells us that we can activate that Conda by using this command here. So we're going to go ahead and activate it. This sadly does not tab complete. And so what's happened is we've typed activate there, and we've moved from base into CLI 101. That's pretty cool. We don't have any special programs installed here yet, but we can actually install programs here using commands from Conda, and you can search those online. For example, if we wanted to install Blast, we could come over here and actually just type in Conda install. And now we give it a channel, which is BioConda, and then Blast. And now it's going to go collect Blast from the internet, ask us if we want to install it, and then sure enough, install it. So now we can type in Blast P -H and get a help menu for Blast. And just like that, you have Blast on your computer when you didn't before. So that's why it's like really useful. And the other thing that's really nice about it is if Conda installs it, it usually works. I don't have problems with things that I install from Conda. So I showed you that, and we'll circle back to it, mostly to explain that whenever you see these environments inside these parens at the beginning of your command prompt, it tells you that you have access to Conda, and that's a great thing. The next bit, we've actually already introduced you to sort of what the command prompt is telling you. It's telling you who you are, who am I? It's telling you your host name, which we didn't do, but you can just type in host name. And host name is just the name of your computer. And you can see that it has a .internal here where it doesn't up here. AWS names them by IP address, so you can see that it actually is going by IP. Obviously, I made this on a different instance than this one. And then here it tells us our working directory, which we can figure out by print working directory. And you can see if we hit pwd here, it shows us sure enough we're in studies, and sure enough we're in studies. This symbol up here is a symbol for home. It's a shortcut. There's many ways to signify home, and we can echo it, and it should tell us what it is. Another way to echo home is there's a variable called home. So there are plenty of shortcuts to home.
Hey, Nathan, I don't want to interrupt. Could you zoom in just a little bit on your command line so the letters are a bit bigger for the people in the room, so the resolution is a little easier for them?
Nice. Is that better?
It probably is. Todd's in the room and says it was just a little bit fuzzy, so now it should be good.
Okay. Good. Okay. So we're still trying to figure out what exactly the command line can tell us about the files we have around us, the environment we're in. So if we cd, not you. Okay, I'm on the right one now. Okay. We cd into module 1 and ls here. You can see that we have access to several types of files here. And we can tell they're different because they have different names. We can also tell some other things without even opening them up by using our ls command. So I've used ls several times, and it's a good time to introduce you. to help. Whenever you are using these commands, most of them come in with a built-in help. If not, they have a built-in man page. I find the help directory is much more intuitive. But if you like manual pages, you can also type in something like man ls, and it's a little more spread out. It's also in a pager and not printed to your standard out. So that's up to you. I've really been enjoying the full help pages recently. So you may have noticed that I used an A flag earlier, and that just lists every file you have that's there. Within Linux and also within Apple, you can hide files by putting a dot in front of them. And we can show you that back here. Let's go to the output. So here I am in output. I'm going to make a directory called sandbox using make dir and call it sandbox. I'm going to cd into sandbox, print my working directory so I can see where I am, ls to see if anything's here, ls -a, and there's these two things that come up. This is the pointer to the directory above. This is a pointer to the current directory. We can make a directory, or we can even we can make another file with the command touch. And so we can say touch my visible file. .text. And sure enough, there it is. We can bring it back and risk writing invisible, put a point in front of it, and ls again. And there is no invisible file. But if we ls -a, sure enough, my invisible file exists. So this is a way that your computer hides files from you. For example, if we go back to home and ls -a, there are plenty of files that you don't just see casually. Your bash history, your bash logout, your bash RC, which is fairly important, as well as your bash profile, and several other types of files. And these are being hidden from you on purpose by this point, but you can see them by typing in -a. So that's one thing that we get out of that. If we go back to studies, we can see some other things. I happen to like ls -thor, and ls -thor gives us a fair amount of information. It gives us our permissions over here. You can see that none of these things are directories because we don't have the D. You can see that as the user and the owner, we have read write permission, but not execute, and that's okay because they're text files. And the group and everyone else has read permissions. It also gives us the size here in human readable form, which is nice. And the R, which I happen to like, shows us the last file modified. So sometimes, and so that last file modified shows up right above your command line, and it's sorted in reverse order. And you can see that from the date that they were made. So these were all uploaded at the same time, and then this was uploaded later. Okay, so that's kind of how to tell where you are, what you have access to, and some things about the files that you have access to. So we're going to take a minute and transition into some file manipulation. But if anyone has any questions, we can take a minute and address those. Okay, that's good. It's a good place to start.
Nathan?
Yes.
Actually, I have a question. How do you end a command line? Like if some command line got stuck, how do you like forcefully end it? What's the command for that?
Oh yeah, Control C. So if we were, so here we go. So there's a command called sleep. It puts your command line or computer to sleep for however many seconds that you type in. So we can type in sleep 1, and that was 1 second. We can type in sleep 10 or 11, ooh, and that's going to be 11 seconds of our life, which feels a lot longer while you're waiting for it. But it's going to come back in a second here. And here we are. And then let's say we feel particularly foolhardy and decide to sleep for however long that is. To end it, we type in Control C and it ends. Maybe you're super attached to your sleep job. You could stop it with Control Z, and then you can put it into the background using BG. And now there's something sleeping in the background, and we can actually probably see it on top. Yeah, it's not going to show up for us. So one last thing about that, I typed in top. We can type in, I think, htop too, which is pretty nice. These are commands that you can use to monitor what's going on the machine. And so it'll give you the process ID, it'll give you the user doing it. You can see that it's even reporting itself, that we're using htop up here. And it gives you all sorts of other information as well. Resources, the time it's been running, the command that's being run. So you could even look down there and look for sleep. Top is a nice way to see if things are working. You can see that it's still sleeping, and it will be sleeping probably for the remainder of our time, unless we bring it to the foreground and then kill it with Control C. So again, the two big takeaways are you can use Control C to kill things, or if you need your command line back because maybe this sleep command was super important to us, you can stop it by typing Control Z. Now it's stopped. It's not doing anything. But you can tell the computer to keep running it by typing BG for background, and it goes into the background. It even gives you the shortcut for doing this. So we could actually just put that command here with that ampersand at the end, and it'll drop it into the background. Now when we list out jobs, we'll have 2 running. And they're both the same job. Right. Awesome. So any other questions?
Yeah. Hey, Nathan. I've had problems downloading bioinformatics programs to an HPC cluster before. You may have mentioned that Conda often does well with install. So could I use a Conda environment to help download a useful program into my directory? Or is that really not what it's used for?
That's exactly what it's used for. So I've used this on HPCs, and I use it currently on our workstation to beta test stuff before we ask our admin to put it on. And we also use a QSub system. So if you're on an HPC, you're submitting your jobs, right? One thing that you have to keep in mind, and it's seriously just a quick Google search, is whenever you put it onto an HPC and you submit it to the queue, you have to activate your Conda in the queue. And so to do that, what you would do is in the middle of your script, you'd write something like source, and then you'd write your bash RC. And because whenever you source your bash RC, you'll notice that my Conda just went back to base. It actually initiates Conda So you have to initiate Conda back. You usually have to initiate Conda back in the middle of your queue submission, and then you Conda activate CLI. There's no, because there we go, CLI 10, and then it would work. So that, yeah, that is something that you can do, that I've done, and it seems to be pretty good.
Nathan,
But
just
also,
a
go ahead.
follow-up to that is every bioinformatics program accessible in Conda or only certain ones?
Definitely not everyone. You have to check. So like we got SAM tools. Hold on.
Oh my goodness, I'm sorry, I didn't hear you.
Okay. I'm in the middle of a meeting right now, so not sure what the point of that was then. Yes, here we are, staying clean in MSU. Yeah, so not every bioinformatics software is on there, but a lot of them are. So for example, yeah,
It's up to the developer of bioinformatics softwares to basically make a Conda package, right?
yes.
I think a lot of the big programs are, but if it's very niche, you might have to do a different kind of install to get it to work.
Yeah, but I mean, even stuff like over to Lumpy and what else has a Conda install? MMSeeks has an install. Yeah, so like, yeah, it just depends on how much the developer wants you to actually use their software. Great. Any other questions? This is good stuff. Okay. Oh, sweet. I thought I saw a hand, but I think we're
Hey,
good
Nathan,
to
a
go.
quick question.
Great.
If you're not necessarily the administrator for your computer, do you have permission to do all this stuff, or you have to get permission from that administrator?
So for installing the Conda, they would have to install Conda for you. But once it's on there, then the point of it is that you can do it without being an administrator. So yeah, so once it's there, it's good stuff. Getting it there does require administrative privileges. So. Okay, we're gonna do a little file manipulation now, and I'm going to be demonstrating head, cat, tail, cut, set, less, more, and rev. So I'm going to CD back to my home directory, list out everything, and you can see that we have our data. Our data is actually going to be stored in studies. We have scripts that live in scripts, and then output is where we're going to put the things that we create. Mini Conda is actually what we're using. We're not using the full version of Conda, and the important detail to that is the full version of Conda comes with a bunch of default programs already embedded, and it just eats up space. So here we are in output. Let's look around. It looks like we've already been here. We've got a Superman FASTA here, a sandbox that we made earlier, a blast example. That's for later. Let's CD into sandbox, because what we're going to be doing now is working with a pretty throwaway text file. So I'm going to copy this throwaway text file from studies into this directory. So CP, and then we're going to go studies, and then we're going to go module. one, and then Origeron Canadensis, not that one. We want examples here. So this command's copy. It probably also has a help. And there's a lot that you can do with it, which is pretty nice. Do you do directories? No difference. Most of what you use copy for is you give copy a name. Give copy a name of the directory that you want, or a thing that you want. In this case, it's a file, and a place to put it, or you could even rename it. So maybe we want to call this example 1A instead. And sure enough, we have a 1A now, as well as a 1. Something to note about copy is that it's destructive. So if you notice at the time on example 1.text is 1844, we can actually do that command again with copy. And sure enough, the time has changed because we overwrote it. Here it doesn't really matter, but do keep that in mind, that copy is a destructive command. Even though it preserves the original file, wherever you're writing it to, it's going to overwrite anything with that name. Move is the same way. So we could actually move example 1A to example 1B.text. And sure enough, we've actually just renamed it. Here we have a 1B instead. Interestingly, it hasn't updated the time that it was written. That's kind of fun. Okay, so now example 1B and example 1, they're a bit redundant. We can get rid of one of those by using rm. Rm is the delete command, and it really does just delete it from your computer. So it's not like trash. You can't undo it. So make sure you know exactly what you're deleting when you delete it. So example 1b.text. And sure enough, it's gone. Okay, well, let's also remove my visible file and my invisible file. Now we're down to just a nice clean directory with example 1 text. So rm is a powerful command. To remove directories, you can use things like rm-dir, and that removes an empty directory. To remove a full directory, you use rm-rf. Now this command should be used sparingly and only when you know exactly what it's pointed at, because it completely deletes it. So if you have raw data that you downloaded from the sequencer and do rm-rf and you don't have a backup anywhere else, it's gone. So I'm always very careful with that command, but sometimes you need to use it. Just always know exactly what it's pointed at. Okay, so now let's look at example _1.text. There's different ways we can look at this. The first one that comes to mind is head. And head will just print out the first 10 lines of the file. Tail will print out the last 10 lines of the file. And you can see we just had, it looks like we have 11 lines in the file. Yeah, oh wait, nope, not 11. We have 13 lines in the file. No, 12 lines in the file. So you can see that it's filled up with a bunch of gibberish, and we're going to use that in a second. The other way we can do it is we can cat. Cat stands for concatenate, and we can do cat example _text and see the whole file. Now, cat's nice. I use it a lot. You can also use, but you can also get yourself, well, not trouble, but you can get into a situation where you have to stop it. For example, if we studied module 1, and then let's say we wanted to look at maybe all the proteins reported for Erigeron canadensis. It'll just scroll across the screen. Whoa, nice. That was super fast. It'll just scroll across the screen and really fill everything up in not nice ways. This would be a time when you could use something like less or more whenever you have these large files. So I'm going to show you that. So instead of catting it to your screen, you can use some other stuff. We'll hit that in a second. Tail cut. Yep. Ooh, cut. Cut's fun because cut actually limits what's printed to the screen. So you can cut based on bytes. So you could take the first 2 bytes of your file, for example, or the first byte of your file. Well, actually, sorry, that's recording the second byte of your file. You can take everything after the second byte of your file and the second byte of your file for each line. And so you can see that really does change things up there. You can also use fields, and fields hone in on tabs. Unfortunately, I didn't include any tabs in this file, but we'll use cut later to actually do some tab stuff. So you could print out, say, a field. You can actually use the delimiter. So we can say a delimiter is a space. And then we want everything in the second field based on the space. And then it'll print out the second word and everything. So cut's really useful. We're going to use it in a bit here. What's our next one? Less or more? So more is nice, particularly whenever we're trying to page through something very large. So you can take it 1 bit at a time. So whenever we stop, we can hit Q and it stops. It returns our command prompt to us, so we can now do new things. But it's left all this stuff on the screen. So that can be quite useful, particularly if you wanted to see what was in the file and use that in your next command. If you didn't need to see what was in the file after you closed out, you could use less. Less is more, except that whenever you quit out of it, you don't actually, it's not printed back to your file, to your screen. The other thing you can do in less, and there's quite a few things, is you can search. So you can search for different characters and it'll highlight them. It'll even jump to them. So maybe you're really interested in the gene 56. Let's see, in that gene. You can actually find it, and there we have it right there. And whenever you quit out, it doesn't have anything left. So, yeah. Let's see what else we've got. Ooh, Rev. So Rev is fun because you can, like, if we echo something, let's say we echo taco, we can also reverse it and get it backwards. So obviously, or race car, it's pretty useless to reverse a palindrome, but somehow fun nonetheless. Why would you use Rev? I use Rev quite frequently, and I use it to get the directory that I'm in, or the name of the file that I'm in. So if we ls here, you can see example1.txt. We could go up one. We're in sandbox now. We go up one more. We're in output now. If we ls output sandbox. We get example1.txt. If we pwd. Okay. So what if we want to get the directory we're in? We're in different directories. We can pwd. We can do something like rev cut minus d. We give it a delimiter, and the delimiter is going to be our file separator right here, /. We want to take the first one, so we'll just type in -f1. And then we're going to, let's see what that gets us. And sure enough, it gets us a reversed word. If we reverse it back, it gives us our current directory. Well, does that still work whenever we go down to output? It does. And does that still work when we go down to sandbox? It does. So this is a really useful command, particularly for whenever you're writing scripts and you need something, and you need the last element of something of an unknown length. This always gets the last element of some string of an unknown length with / as delimiters. So rev is quite useful. It's also fun to see what it does with taco cap. Okay, so that's kind of how we do some basic looking at files. The other bit for looking at files is, did I include that yet? Is you'll want to use a text editor. Nano's a common text editor. It's also a good one to start on. Currently, I've been working with Vim. Vim, whenever you open it up, it gives you all sorts of information like how to quit, which is good, how to get help. And then it also should have a Vim tutorial that you can log into. And if you spend about, for the small price of a couple hours, you can have a fairly useful text editor that you can navigate through quite well. The other one, and I'm not sure if it's on here, but I don't know how to, is Emacs, and I'm not going to touch that. It's been a while since I've worked with Emacs. But those are other ways to manipulate texts and files on your command line. So we're going to transition to searching files, and we're going to start with egrep. But before we go on, did anyone have any questions about navigating?
Nathan, I saw you using lots of pipes there to chain commands together. Do you want to just quickly touch base what pipes do and chaining commands?
So what pipes do is they allow the output from one command to be caught and used by the next command. So whenever we type out pwd, print working directory, we can pipe that to rev, and rev will actually automatically catch the output. Rev is its own command, and it can actually just reverse all of a file as well. But whenever we chain something together, whenever we chain it to pwd, we don't have to give it a file. It actually can figure out where it's coming from. And the same is true with cut. Cut is its own command and it's its own program and can take files from the command line, or it can catch output that's being printed to standard out and use that. So that's where the cut command comes in. There, and then again, we're piping it to rev. So piping is really quite useful, particularly as you build things, and it begins to become very intuitive that way. This also works with several of the bioinformatics programs, such as SAM tools and BED tools, are designed for piping as well. And we're moving on to egrep next, and egrep also is good with piping, so it's good stuff. So let's start by when we get a new command. I habitually use egrep. Grep was the one I learned on. Egrep and grep are the same thing. Whoop. And it's up to you which one you'd like to use. So I tend to like egrep because what it does is it gives me access automatically to extended expressions, sorry, regular expression patterns, matching within my grep search. Regular expressions are a way to represent patterns, and we won't get into regular expressions just yet, but we will touch on them later if we have time. So it's up to you if you want to use egrep or grep. They're the same. So now what we're going to do is do a series of samples where we take, where we egrep or grep hello against our example text. So let's clear this off so that it's not so visually jarring. You can type in clear, and it just, all it's doing is moving stuff up. It's just moved the command line up to the top of the screen. So we can egrep hello and type example.text. And egrep does this nice thing where it shows the match in color. And notice how it's matching. It's matching very much like Control F does in a Microsoft Word document, except that it is case sensitive. See that it picks up this hello, but not that hello or that hello. It's also directionally sensitive, but that would be disappointing if it weren't. It finds it in fragments, or it finds it if it's the fragment of a final word. If we do egrep minus W, what happens? Okay, well, that's interesting. Hello one disappears, but hello dot one does not. And this is a quirk of the bash environment. The bash environment is really good at recognizing standard separators. And so if you use a period, potentially if you use an underscore, it'll still match as a word. So here we've got hello that's matching all the way across here, but hello one is not, because it sees that as a different word. Whereas it sees this period as ending a word. And so sure enough, it just matches hello. We can also count with grep. And it gives us back 6. If we come back up here, we can actually get a sense of what it's counting for, because all we've added is this counting flag. And here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 total hellos, but it only counts 6 because there's only 6 lines with hello on them. And so that's something that's pretty critical to recognize whenever you're counting with grep, is that it's only counting the lines on which it occurs. So what does egrep, what does minus I do? Okay, let's see. It makes it case insensitive. So minus I makes it case insensitive. What does Z do? I ran into this while I was reading the help menu, preparing for this. It actually searches across line breaks. I was really excited because I thought you could really sort of extend this quite a bit, but this is about the extent of what you get back. Is you can find a pattern that's broken up by a line break, but it won't extend regular expressions across line breaks. I tried really hard. What does egrep minus n do? Let's have a look at that. It reports the line number it's on. And so by reporting the line number, this can be helpful if you're trying to find where something is, or just figure out how far through the file you have to get first. If we egrep minus h, well, let's try this. Egrep hello star. And what the star does is says grep search for hello in any file in this directory. Well, there's only one file in this directory, so that doesn't really help us much. But if we cp example 1 to decoy text, we can try this command again. And sure enough, we have a decoy, and then we also have an example. And so it's reporting to us, whoop, right there. So it's reporting to us on which file it's found in. Sometimes you want to search without regard to if, and you don't want it to report if the file name at all. And so you can use the -h to in fact suppress the file name at the end. And so this is, there's one last thing to show, and that's sort of a rudimentary regular expression. What I'm saying here, what I'm telling grep here is search for hello, and then any 5 characters after that, report those back from example.txt. And so now you can see that this is our match. Egrep hello there, egrep hello hell, hello whirl, hello one.e, and so forth. And so this can be really useful if, say, you know that you want something and you don't know its name, but you know that it's close to something. So this can be quite useful. The other thing you can do is you can give it bounds as well. So you can do 0 to 1. And now you can see that we get a couple results that we didn't, couple matches that we didn't get before, namely hello and hello 1. And those weren't up here because there weren't 5 characters between hello and the end of the line. So that's a rudimentary regular expression that they're quite helpful. And there's something to keep in mind for whenever you're having to look at for very specific data. Okay, we're going to finish out with creating files and directories. See how we're doing on time. All right. Oh man. Okay. So we're gonna go through this a little bit fast, but there's not a whole lot to it. You've already seen me use make directory. So let's talk about different ways to put things into a text file. So we have decoy text1, decoy_1.txt, and example_1.txt. And both of those were previously existing or copied from something that previously existed. One of my favorite ways to create a new file is to cat redirect, which is this greater than sign, and then example2. Give it a file name. And now anything we type into the command line, this is my new file. So anything you type in there is committed. Now, if I wanted to go back and fix my spelling mistake, you can see that my command line is not agreeing with me. I'm trying to up arrow and fix it, and I can't. And that's just how it works. But we can stop And once we've stopped, we can cat example2 text back to the screen. And we can see that we have, this is my new file, this is my new line, and this is a spelling mistake. What if we wanted to fix that? Well, we could log in with something like nano and do example2 text, come down to spelling mistake, and fix it. So how do we get out of here? Well, we can exit by pressing Control X. It asks us if we want to save. The answer is yes. That's how we want to write it. Now we can cat our example_2.txt to the screen, and our spelling mistake is fixed. So other ways to do that would be Vim or Emacs, and I'll leave that to you to explore, but I do encourage you to explore Nano's just the beginning of the world of fun of command line based text editors. Make directory is just another way to make it, is the way that we make directories. We can make directory temp and ls-store. Sure enough, it's a directory and it'll be empty. We can remove a directory using rmdir temp, and sure enough, it removes the directory. We covered copy and we've covered move. Let's go ahead and make a directory temp again, and temp is back. We can move decoy text into temp. And the way we do that is we give it the name decoy text, and then we give it where we want it to go. If we give it a directory name, it moves it into the directory. If we give it a file name, it renames it to that file. So just keep that in mind. So sure enough, decoy.txt is missing. We can list out temp, and there it is. Well, let's remove directory temp because we don't need decoy anymore, and we don't really need our temporary directory. Uh-oh. So remove directory fails because it's not empty. That's nice because it tells us that remove directory is a fairly safe command as far as remove commands go. And the reason it is because it'll give you these warnings before you, like, I don't know, delete an important directory that you didn't look at. We happen to know what's in there, so we can use rm-rf temp. And sure enough, it's gone. So we've got example1 and example2 now. And those are the basics of creating files and directories. There's one more thing with the redirect. You can cat, like, let's say that we wanted to put example1 and example2 together to create example3. We can cat example1, example2, and then we could put that into example3. So what we're doing is we're writing both of these things to standard out, catching them, putting them into a new file. What if we wanted to put these all back together to create, like, maybe we want an example4? Well, instead of writing them all out, we can use the asterisk to expand. And we can see what we'd catch with that by listing everything. And sure enough, everything that has example is listed. For example, it has to match. So if we use non-example star, it doesn't match, but if we use example star, it does match. So ls tells us what to expect. We can cat those all together, and we can put them into example4. So now we can less example4.txt, and sure enough, we're getting quite a long file now. Quit out of that. So the last thing to know is that we, instead of just overwriting it with a single, we can append to it with a double redirect. So we can cat example 4 dot text, and this line ended. And then we can see what that looks like, cat example 4 dot text. And we can see that we did append a line at the end. And so those are the basics of reading, writing, and creating some files. Next up, we're going to go through some case studies. But before we go to that, if anyone has any questions, this would be a good time to take a little break and address those.
So Nathan, the little greater than sign, you're calling it redirect. So where is it redirecting it from, or to, and where's it redirecting it from?
Okay, so what it's doing is it's redirecting things from standard out. So if we look at the help documentation for cat, it concatenates standard input to standard output. So it takes something that you've given it and it puts it on standard output. Standard output is just your terminal screen. There's also standard error on your terminal screen as well. Standard error is where programs write warnings to, and they're not caught by standard out. So let's see if we can, trying to think of how I can make a standard error. We won't for now. But if you wanted to catch standard error, cat hello text. Oh wait, we can do it like that, head. Okay, so see, head actually has reported something back to us. What if we wanted to hello out? See, it doesn't catch that because it hasn't written it to standard out. It's actually written it to standard error. To catch standard error, you need to write a redirect with a 2 in front of it. And then we can cat hello error. So standard output and standard error are the kind of 2 channels to think about whenever you have a command line situation. Most of like what's in files, most of what's printed to screen, you'll catch with the redirect or the greater than sign, and that catches it and it'll put it into a file named whatever you name it, or appended to wherever you point it to. Standard error is the other one. Sometimes you have to write these. So just keep that in mind, that if you write a redirect and it's still printing stuff to screen, where it's printing is not to standard out, it's actually printing to standard error.
Thank you.
Yeah. Okay, in the time remaining, and I want to check on this, it looks like we've got about, that right? Just 15 minutes, 15 minutes or so left till 3:30. And if I remember the schedule, that's where we're stopping. So we'll see how many of these case studies we can get through. And I'll sort of lay out how you can use the command line to cull through data. So I'm gonna take a sip here real quick. So. Okay, here we go. First of all, we can cd back to home. We can confirm we're in home by typing print print working directory. List out where we want to be. We want to go into output, so we're going to cd into output. Okay, so we're not working in Sandbox anymore. We're doing case studies. We could do blast example, or we could just give them each name. So we could start with make directory protein set. Actually, so if we go into cytochrome P450s, and the reason I named it cytochrome P450s is I didn't advance my slide yet. What we're going to do is we're going to use the output of Interpro scan run on a computer and actually pull out everything in the cytochrome P450 superfamily that has the accession IPR036396. And that should correspond to everything that has been identified by Interpro as part of the cytochrome P450 superfamily. So how can we do that? First of all, I want to show you a little bit about the cytochrome P450, about the Interpro scan output. So we're going to copy that from studies. And I happen to know that it's in module 1 and that it's in Origeron canadensis IPR scan.psv. Takes a second to copy. We can list out, and sure enough, here it is. I'm going to less it. Here, once we give it that. Okay, so this is like basically unreadable in its current format. To fix that, we're going to type in -s, and it's going to chop the lines for us. Now we can read it, which is nice. To see the rest of each line, we use the over arrow. In that case, that's going to be your right arrow. And you can just arrow over. So you can see here that it's got in the first name, the first column, there's a name, and the second column, it's giving us some sort of information. We can actually look that up, but it's not really super important to us right now. Here in this column, if you follow it up, this is actually the database that was used. And then the results from that database. One thing to note is that each gene has multiple things reported for it. So gene 10282 has multiple lines. And the same with gene 24296. So that's not like super important to us yet, but it will be. Something else to consider is that as these are reported, let's see, only some of them actually get the IPR accessions or the Interpro accession numbers. The Interpro accession numbers happen in column 12. The gene name is in column 1, and then the Interpro description is in column 13. So we can actually do some pretty cool stuff to make it even more readable. So we can say cut and give it a list of columns that we want to look at. And let's see, we want to call them fields, though, -f. Well, that's kind of nice. And then, so this is where we could use a Control-C. And so sure enough, we can get a whole lot of things out, and we can get the IPRs out as well. Well, how do we get just the IPRs for the cytochromes that we're interested in? Well, we can start actually building a command here. So we can say egrep and then give it our IPR number. So it'd be IPR 03636396. And sure enough, there we are. We get our nice match. It's colored red here. And then we get our description next to it, confirming that we did okay. It looks like we've got some repeats. Well, that's not super useful. How can we fix that? We can fix that a couple ways. We can, well, the easiest way is going to be using a command combo called sort and unique. So sort and unique, what that does is it collapses everything that's identical that's right next to each other in terms of the line. So for example, if we cat sample, so if we unique sample here, see how it goes to ABA? It's because all these A's are next to each other, so they're collapsed into one A. All these B's are collapsed into one B, and all these A's are collapsed into one A again. And they're not collapsed, all the A's aren't collapsed together because it's only what's right next to each other. However, if we sort sample and then unique it, we only get A and B. So by adding sort and unique to the end of this, what it does is it should give us only unique instances and only unique gene names, because if it comes with this IPR, it also only has this description. And so the only thing that's changing is the gene name. Well, we could eyeball it and like scroll up and down the screen and try to figure out if it's right, or we could just count the lines using WC, which is the program for word counting, and -L says just report to us the line number. And so that gives us 348, and before we were looking at 749. So we've really collapsed quite a bit of redundantness. So what else can we do here? Well, we could get a list of genes, as it turns out. We could use cut again, -F, and say field 1. And how are we doing on our sort unique? It all looks present and correct. We can count again to see if anything's changed, which it wouldn't have because we're doing it after the fact. Let's go ahead and do this. Cut -F, 1. And sure enough, even whenever we just do the gene name, we still get the same number, which is nice. Well, what if we want to capture all those in a list? So we can say CYP 450 superfamily list. We can count everything in the CYP list, and we get 348. Well, let's see what that got us. We can head that. We don't have to look at all 348. Okay, so, oh man, we're almost done. I didn't even get to show you my SAM tools trick. Let me show you the SAM tools trick, and then we'll be at a nice stopping point. So we have a list of proteins. You probably want to get those proteins out. The easiest way to get them out is to use SAM tools. So if we kind of activate SAM tools, we can actually use the command SAM tools FASTA index, which is FAIDX. We give it the FASTA name. It's going to be studies module 1, Erigeron canadensis AA. And then we give it actually a region or a file. So if we use -R, we can give it a file that's filled with regions or just names of contigs, and it'll pull those names of contigs for us. So we can do that with our CYP50, and then if we give it an out, we can give it a CYP50. Looks like we're going to have to build the FASTA first. Oh, you know what we have to do? We have to copy that there because that Control-A, E, Control-Y, so we can bring that back. So you can see that, oh, yeah, we didn't do that. Let's look at our less. So if we look at our less CYP, let's do it this way. Let's egrep our FASTA headers out of our CYP 450 SF FASTA, and then count those. That's going to tell us if we got all our FASTAs back. And sure enough, we did. So that's a basic way that you can use SAMTools FASTA to take a list of proteins and get them out of another FASTA. So we ran a little short on time, but obviously there are other things we can do with it.
All right.
So any questions? Yeah, go ahead.
I'm gonna get the shepherd's crook out because I think the next one's about to start.
Okay, I think we're done.
So if anyone has any questions for Nathan on the tutorial, don't be afraid to send an email or set up a Zoom call with him at some later point. Thanks, Nathan.
Thanks, guys.
Thanks, Nathan. Yeah, can we give him a round of applause?